Okay, so we have this reference-based tree implementations or the array-based tree implementations. That's the structure of the binary heap. And if we are going to do the insertion of the binary heap, how can we do that? We know that where to put the next value itself so that we can keep the complete tree constraint, the shape property. However, we also want to keep the heap property. And to keep heap property, we need a certain insertion operation process. That's called percolate up. So, for example, what's this percolation means? Percolation is actually, so if it rains here, and we have much of the water, and this is the rain, and water here, and water is going to be percolate down here. So you see this percolation here. The percolation means that it percolates through a certain element, goes through a certain layers to reach to a certain location. That's the percolation. And that's this is the downward process. This is so it's called percolation down. And what we are going to do to keep the heap property in the binary heap is percolate up. So how to perform the percolate up? First, we start from the root node because that is a natural place to insert the next node to keep the complete tree constraint. And then we approach to the root of this approach toward a root. And how to insert a value at the next node to insert. So first we insert the value here. Insert the value at the last index of the array, and then compare the value to the values of the inserted node's parents. So compare this node value to the parent node's value. So the heap property is parent value is always bigger than child value. That's the max heap property, right? And then let's compare it. 3 and 70. This is the heap property is broken here. Then what we are going to do is exchange the two values. Exchange the two values like this. 70 goes up and 3 goes down. And you can see that we put 70 here. We put 70 here like this rain, and it percolated up. It percolated up. The percolation happened downward here. Here, percolation happened upward. So 70 percolated up and 3 percolate down. And until, keep doing this until it reach to this heap property is met, right? So 73. And next percolation is that 70 goes up and 19 goes down because that 19 is smaller. So 19 is actually smaller than the 70. So heap property is broken. So 70 is going to be percolate up like this. And then we compare the 99 and 70. Actually, now is perfect time that heap property is kept, so there is no more percolation up. So now we don't have no more percolation, and now we have a binary heap that has a new value of 70. So when we inserted 70 here, we kept the shape property, but the heap property was broken. So by going through this process, now we have, by going through this percolation up process, now we have 70 in the right place, and the heap property and the shape property both are not broken, right? So that's how we insert a node in the binary heap. And how to delete a node in binary heap? Actually, deletion operation of the binary heap is always taking a root. Why is that? Because binary heap we originally intended to utilize to implement the binary queue. So this is the basis data structure for this priority queue. And priority queue always take the maximum or the minimum value of it. And here we are going to implement the maximum value of the as a higher priority because that we are utilizing the binary max heap. So next element to get out from this priority queue is the 99 in this binary heap. So it's always going to take the root. And after taking the root, how can you delete the 99? After this 99 is gone, then the root is empty. How to fill in this root? So that's the key of this delete operation. And this delete operation is the, in other words, percolate down operation. And how to do that? First, we are going to take the 99 away, right? And then delete the root value and replace the root value node with the last node. So the last node, if we keep tracking the tree size, we know where it is in the array, right? So we can easily access to this value 1 because that is the last value. And when the 99 is gone, we put that 1 up here. That's one thing we do. And then the next thing is that compare the value to the value of the inserted node's children. So compare this 1 with the inserted node children, 19 and 36. 1, 19. That's bad. Its heap property is broken. 1, 36. That's bad. Heap property is broken. Then what you're going to do, if the children's value is bigger than the parents, then pick a bigger value and exchange it. For example, in this case, 36 is going to be picked to replace the 1, to exchange the value with 1. So 36 is going to go up and 1 is going to go down. Why we pick the bigger value between the children? Because that if we pick the 19 goes up, then it means that its heap property is still broken because 36 is still bigger than 19, right? So we need to replace it with the bigger value in the children. So 36 is going to go up and 1 is going to go down. So after doing that, the 1 is going to be located around here. So it's percolate down, right? 36 is up and 1 is down and 1 is percolated down. So it's called percolate down process. And after that, 1 is compared to 1. That's not good, but okay. So 1 to 5. Oh, that's not good. And to find out a bigger value is 25 actually. So we need to exchange this 1 with 25, and then 1 is located here and 25 is now located here. Now it's complete tree as well as keeping the heap properties. So this 1 was actually here, brought back to here and percolated down to this location, right? So that's the delete operation of the binary heap.